Welcome to Auto Intelligence. I'm Steve with my morning espresso in hand, ready to dive into what might be the most consequential story in automotive history.
And I'm Claire, part of the Auto Agentic team alongside Steve. I've got my double shot ready too, and trust me, we're going to need it today. What does a 1950s academic conference have to do with the car you'll be driving in 2030?
Everything, as it turns out.
Before we begin this journey, we want to express our sincere gratitude to our growing audience. The response to Auto Intelligence has been phenomenal, and your feedback continues to shape our content. New episodes drop every Tuesday, Thursday, and Saturday, and we're thrilled you're along for the ride.
Today, we're tackling a question that will determine the future of every vehicle on Earth. In an AI world dominated by two superpowers with radically different approaches, who will control the brain of your next car? Will it think like Silicon Valley, coordinate like Shenzhen, or could it potentially reflect a third way, one pioneered in the research labs of Toronto?
Because what we're really talking about isn't just geopolitics or abstract tech policy. This is about who controls the fundamental technology that will power everything from your personal vehicle to the entire transportation ecosystem around it.
And to understand this high-stakes game, we need to go back to where it all began. Not in a sleek Silicon Valley campus or a gleaming Chinese tech hub, but in the modest hallways of a Canadian university where the modern automotive brain was born.
Most people think artificial intelligence started with ChatGPT or maybe IBM's Deep Blue chess system. But the technology that powers your car's ability to recognize a stop sign or detect a pedestrian traces back much further, to the late 1950s and the birth of AI as a field.
The term artificial intelligence was coined at a workshop at Dartmouth College in 1956. The participants believed they could create machines that could think like humans within a generation. They were a bit optimistic.
To put this in automotive terms, while this was happening, cars still had carburetors and drum brakes. The idea that they would someday drive themselves was pure science fiction.
The early AI pioneers tried to program explicit rules and logic into computers. If you wanted a computer to recognize a stop sign, you'd have to program exact rules about red octagons and the letters S-T-O-P.
Which works fine until the stop sign is partially obscured or covered in snow or viewed from an angle. The rule-based approach quickly hit its limits.
This led to what's known as the AI winter, a period in the 1970s and 80s when funding dried up because AI couldn't deliver on its promises. For the tech world, it meant slashed research budgets, but for the auto industry, it had direct consequences.
Absolutely. Promising R&D in early autonomous systems at General Motors, Daimler-Benz, and research universities was shelved, seen as a dead end. Those cancelled programs set automotive autonomy back by a decade, a deficit the industry is still working to overcome.
But in this frozen landscape of the AI winter, one researcher in Toronto was planting seeds that would eventually transform not just AI, but the fundamental way every modern vehicle perceives the world.
Geoffrey Hinton, a British-born cognitive psychologist turned computer scientist who joined the University of Toronto with a radical idea. Instead of programming explicit rules, what if machines could learn patterns from data, the way human brains do?
Hinton was working on neural networks, mathematical models loosely inspired by the human brain. His idea was that instead of programming a computer to recognize a stop sign with rules, you could show it thousands of images of stop signs and let it learn the patterns.
Which might sound obvious now, but in the 1980s and early 90s, most of the AI field had abandoned this approach. It was considered a dead end.
Canada deserves enormous credit here. While American research institutions were chasing other approaches, the Canadian Institute for Advanced Research, CIFAR, and the Natural Sciences and Engineering Research Council of Canada, NSERC, funded Hinton's work when almost no one else would.
And this wasn't just academic curiosity. Even then, there were visionaries who saw the potential applications in automotive systems. Carnegie Mellon's Alvin, autonomous land vehicle in a neural network, project in the late 1980s, was using early neural networks for lane detection, a direct precursor to today's lane-keeping assist systems.
The fundamental problem these researchers were trying to solve was perception. How does a machine or a vehicle make sense of the visual world? How does it distinguish a pedestrian from a lamppost, a lane marking from a random crack in the pavement?
But progress was painfully slow. Neural networks were promising in theory, but in practice, they were computationally intensive and data-hungry, in an era when both computing power and data were scarce.
Everything changed in 2012. That's when Hinton and his students, including Ilya Sutskever, who would later co-found OpenAI, and Alex Krzyzewski, entered the annual ImageNet competition with a neural network-based model called AlexNet.
The ImageNet competition was a global challenge to classify objects in millions of images. Previous winners had error rates around 26%. AlexNet came in at 15.3%, an improvement so dramatic it shocked the entire field.
When Geoffrey Hinton and his team won that 2012 ImageNet competition, they didn't just prove a computer could identify a cat in a photo. They proved the core principle that allows a modern car to distinguish a pedestrian from a lamppost at 50 miles per hour.
That academic victory is the direct ancestor of every driver assist system on the market today. Tesla's Autopilot, GM's Super Cruise, Ford's Blue Cruise, they all rely on neural networks similar to what Hinton's team pioneered.
Within months of the ImageNet breakthrough, Google hired Hinton and his entire team. Not just for search or advertising, they wanted this technology for their nascent self-driving car project, which would eventually become Waymo.
And that's where we see the first key divergence in our story. While Canadian researchers invented the foundational technology, American companies commercialized it at massive scale. Silicon Valley quickly recognized that neural networks weren't just useful for image recognition, they were essential for autonomous vehicles.
This is a critical point. The technology that would eventually power self-driving cars didn't come from automotive engineers or traditional Tier 1 suppliers. It came from academic AI researchers in Toronto who were trying to understand how machines could learn.
And that's been a persistent challenge for traditional automakers. They had to adapt to a technology that was developing outside their traditional R&D ecosystem.
Companies that understood this early, Tesla, for example, gained a significant advantage. Tesla hired AI experts, not just automotive engineers, and built an internal AI team focused on computer vision and neural networks.
Meanwhile, traditional automakers often found themselves playing catch-up, forming partnerships with tech companies or acquiring startups to gain access to the talent and technology they needed.
But the story doesn't end with America commercializing Canadian research, because in March 2016, something happened that would wake up a sleeping giant on the other side of the Pacific and fundamentally alter the trajectory of automotive AI.
AlphaGo versus Lisadol. On the surface, it was a match between an AI system and a human champion of Go, the ancient Chinese board game, with more possible positions than atoms in the observable universe.
But what made this different from previous AI milestones like IBM's Deep Blue beating Garry Kasparov at chess was the nature of Go itself. Chess can be approached with computational brute force, calculating all possible moves. Go requires something more like intuition.
And AlphaGo displayed not just computational power, but a kind of creativity that stunned experts. In Game 2, it made a move 37, that human commentators initially thought was a mistake, but turned out to be brilliant.
In the West, this was celebrated as a technical marvel, a testament to DeepMind's reinforcement learning algorithms. But in China, it was viewed as something much more profound.
The match was broadcast live across China. Millions watched as this AI system, developed by a Google subsidiary, defeated one of the world's greatest Go masters in a game with deep cultural significance in China.
Chinese state media described it as a Sputnik moment, a reference to the 1957 Soviet satellite launch that shocked America into the space race. If the United States had launched the AI equivalent of a space race, China was now jolted into action.
And here's where the automotive connection becomes clear. Within 3 months of AlphaGo's victory, the Chinese State Council issued one of the most ambitious technological declarations in modern history. By 2030, China will be the world's primary AI innovation center.
This wasn't just rhetoric. The new generation artificial intelligence development plan that followed explicitly identified intelligent vehicles and transportation as key domains for Chinese leadership.
The plan allocated billions in funding for autonomous driving research, smart transportation infrastructure, and the development of AI chips specifically designed for automotive applications.
It also established clear mandates for cities to serve as testing grounds for these technologies. Hangzhou, Shenzhen, Beijing, Chengdu, these became living laboratories for automotive AI deployment.
What made China's approach different from the West was its comprehensiveness. They weren't just developing autonomous vehicles in isolation, they were building the entire ecosystem those vehicles would operate in.
Exactly. When Hangzhou deployed Alibaba's city brain system in 2016, it wasn't just an interesting tech demo, it was a fundamental rethinking of urban transportation. The system used AI to manage traffic lights based on real-time video analysis from thousands of cameras.
The results were immediate and tangible. Average commute times dropped by 15 to 20% during the pilot years. By 2020, the system was managing over 1,300 traffic lights across the city.
And this is where we see a key philosophical difference emerging. While American companies like Waymo and Tesla were focusing on making individual vehicles smart enough to handle any situation anywhere, China was making the entire transportation system intelligent.
The Chinese approach recognized a fundamental truth. It's easier to build an autonomous vehicle that can navigate a smart city than it is to build one that can navigate any environment without external support.
This is such a crucial distinction. In the American model, the vehicle needs to be a self-contained superintelligence. It needs to handle unpredictable pedestrians, unusual road conditions, construction zones, all on its own.
But in the Chinese model, the vehicle is just one node in a network. The traffic lights communicate with the car, the road infrastructure shares data, other vehicles broadcast their intentions. The burden of intelligence is distributed.
And this directly impacts the kind of AI and sensors needed in the vehicle. A Waymo vehicle in Phoenix needs an expensive array of LiDAR, radar, cameras, and powerful onboard computers to make sense of an unpredictable world.
While a Chinese autonomous vehicle operating in a smart city environment can potentially use fewer sensors and less computing power because it's receiving so much information from the infrastructure around it.
This approach has significant economic implications. The American model produces vehicles that cost hundreds of thousands of dollars with all their sensing and computing equipment. The Chinese model potentially reduces that cost by offloading some intelligence to the infrastructure.
And it creates a very different path to deployment. American autonomous vehicles typically start in constrained environments, specific neighborhoods, mapped areas, good weather conditions, and gradually expand their operational domain.
Chinese autonomous vehicles can potentially deploy more widely from the start in areas with supporting infrastructure, then gradually reduce their dependence on that infrastructure as their capabilities improve.
By 2020, this philosophical difference was producing tangible results. In Guangzhou, Baidu's Apollo robotaxis were operating in a 144 square kilometre area with the support of 5G-connected infrastructure, significantly larger than most Western autonomous vehicle deployments.
Meanwhile, Shanghai was rolling out a network of smart roads with embedded sensors and communication systems specifically designed to support autonomous vehicles.
All of this was happening with extraordinary speed because of China's whole-of-nation approach. Local governments, technology companies, and research institutions were all aligned toward the same goal, establishing China as the global leader in automotive AI.
But the story gets even more interesting after 2020, when geopolitical tensions and U.S. export controls forced China to take a truly unexpected turn in its automotive AI strategy.
In 2022, the United States imposed significant export controls on advanced semiconductors and AI technology to China. The restrictions specifically targeted chips like NVIDIA's A100 and H100 GPUs, the exact hardware needed to train large AI models.
The intent was to slow China's AI progress, particularly in sensitive areas like facial recognition and surveillance. But it had a fascinating unintended consequence in the automotive AI space.
Instead of slowing down, China pivoted to a radically different approach, one that emphasized efficiency, openness, and distributed development over the centralized, resource-intensive models favored in the West.
This is a critical moment in our story. When faced with limited access to cutting-edge AI chips, Chinese companies could have simply tried to replicate American hardware. Instead, they reimagined the entire development model for automotive AI.
The most visible manifestation of this pivot was the explosion of open-source AI in China. Companies like DeepSeek, Baidu, and Alibaba began releasing sophisticated AI models, including automotive-specific models, under permissive licenses.
Take DeepSeek V2, for example. It's trained on both Chinese and English. It's competitive with models like GPT 3.5, and it's completely open. But more importantly for our audience, it includes specialized modules for autonomous driving, traffic optimization, and vehicle-to-everything communication.
Or consider Baidu's Apollo platform. It's not just open source software, it's an entire autonomous driving ecosystem. Hardware specifications, sensor fusion algorithms, path planning software, even simulation environments. Any automaker can download it and build their own autonomous vehicle.
This open source approach stands in stark contrast to the American model. Waymo's self-driving technology is a closely guarded corporate asset. Tesla's full self-driving system is proprietary. Even the datasets used to train these systems are considered competitive advantages.
The strategic implications are profound. By making their automotive AI platforms open and accessible, Chinese companies are positioning themselves as the foundation for a generation of vehicles worldwide.
It's very similar to what Google did with Android in the smartphone space. Android is free and open source, but Google services are built into most Android phones. China's betting that if their AI becomes the standard for autonomous vehicles, they control the ecosystem.
And it's already working. We're seeing automakers in Southeast Asia, Africa, Latin America, and even parts of Europe building their autonomous vehicle programs on Chinese open source platforms. Not because of political alignment, but because of practical considerations: cost, accessibility, and flexibility.
Let's use a specific example to illustrate this. In 2023, Indonesia's Astra announced a partnership with Baidu to develop autonomous public transportation using the Apollo platform. They're not just buying a finished product, Indonesian engineers are customizing the system for local conditions.
The roads in Jakarta present unique challenges. Complex traffic patterns, a mix of vehicle types from motorcycles to buses, seasonal flooding that changes road conditions. The open source nature of Apollo allows them to adapt it specifically for these conditions.
Meanwhile, a comparable Western system would likely come as a black box, a finished product that can't easily be modified for local conditions, and it would probably cost significantly more.
This difference in approach creates a fascinating dynamic in the global automotive market. Western systems may be more advanced in absolute terms, but Chinese systems are often more adaptable and accessible.
And this directly impacts automotive manufacturers' strategic decisions. Do you partner with an American tech company for a cutting-edge but proprietary system? Or do you build on a Chinese open-source platform that you can customize for your specific market?
For many global automakers, the answer increasingly depends on their target markets. If they're primarily selling in North America and Western Europe, the American approach makes sense. If they're focused on emerging markets, the Chinese approach offers clear advantages.
But there's another dimension to this that's often overlooked: the data flow. An autonomous vehicle generates terabytes of data every day. Camera feeds, sensor readings, traffic patterns, passenger behavior. All of that data is valuable for improving AI systems.
In the American model, this data typically flows back to the company that provided the autonomous driving system. Tesla collects data from its vehicles to improve autopilot. Waymo collects data from its robotaxis to refine its algorithms.
In the Chinese open source model, the data flow is more complex. The base technology may be open, but companies building on it often establish data sharing agreements with the original developers.
So when a country adopts Chinese automotive AI platforms, they're not just choosing software, they're choosing which AI ecosystem gets access to their transportation data. This has significant geopolitical implications beyond the automotive sector.
You're listening to Auto Intelligence, brought to you by AutoAgentic, the platform transforming automotive retail with intelligent, human-centered AI. While we're discussing these massive AI ecosystems that are reshaping global transportation, it's worth remembering that AI is transforming every aspect of the automotive industry, including how vehicles are sold and serviced.
AutoAgentic isn't just about automation, it's about augmentation. It provides dealerships with over 90 specialized AI agents that help sales teams better understand customer needs, optimize inventory, and create more personalized experiences. Now, back to our exploration of the global AI race and its impact on the future of automotive technology.
Let's dig deeper into the technical differences between the American and Chinese approaches to automotive AI, because they reflect fundamentally different visions of how autonomous vehicles should work.
At the core of the American approach is what we might call the super-intelligent vehicle. It's a self-contained system that relies primarily on its own sensors, computing power, and AI to navigate the world.
Companies like Waymo and Cruise equip their vehicles with an impressive array of sensors. A typical Waymo vehicle has multiple LiDAR sensors, radar, cameras, and ultrasonic sensors, all generating massive amounts of data that needs to be processed in real time.
And the computing power required is extraordinary. Waymo's vehicles contain custom-designed computers capable of performing trillions of operations per second to make sense of all that sensor data.
The AI systems behind these vehicles are typically trained on enormous data sets, millions of miles of real-world driving supplemented by billions of miles in simulation. They need to encounter every possible scenario, from rare weather conditions to unusual road configurations.
The result is a vehicle that can theoretically operate anywhere without any special infrastructure, but it's extraordinarily expensive and technically challenging to develop.
In contrast, the Chinese approach emphasizes what we might call ecosystem intelligence. Instead of putting all the intelligence in the vehicle, they distribute it throughout the transportation system.
A concrete example, in Shenzhen, traffic lights are equipped with AI-powered cameras that detect vehicles, pedestrians, and road conditions. This information is broadcast to approaching autonomous vehicles, giving them advance warning of conditions they can't yet see with their own sensors.
Or consider Guangzhou's Vehicle Infrastructure Cooperation System. Roadside units equipped with sensors and communication systems create a digital twin of the traffic environment. Autonomous vehicles tap into the shared perception, effectively extending their sensing range beyond their physical sensors.
This approach allows Chinese autonomous vehicles to operate with fewer onboard sensors and less computing power. They don't need to be super intelligent because they're part of an intelligent system.
The technical implications are significant. American autonomous vehicles typically require high-definition maps created through a process called mapping and localization. The vehicle compares what it sees to a pre-existing map to understand precisely where it is.
Chinese systems increasingly rely on what's called V2X, or vehicle-to-everything communication. The vehicle receives information from other vehicles, infrastructure, pedestrians, smartphones, building a real-time understanding of its environment without necessarily needing pre-existing maps.
This difference extends to the AI models themselves. American companies tend to use larger, more comprehensive models trained on massive datasets. These models need substantial computing power to run.
Chinese companies are increasingly focused on smaller, more efficient models, specifically designed to run on limited hardware. They compensate for the model's limitations by supplying them with more structured, pre-processed information from the environment.
And this directly impacts the type of chips and computing architecture needed. Western autonomous vehicles often rely on power-hungry GPUs or specialized AI accelerators. Chinese systems are increasingly designed to run on more power-efficient chips that can be manufactured domestically.
By 2024, Huawei's Ascend AI chips and high-silicon automotive processors were powering a growing percentage of Chinese autonomous vehicles, reducing dependence on Western technology.
But perhaps the most interesting technical divergence is in how these systems learn and improve. American autonomous vehicles typically follow what's called a collect, train, deploy cycle. They collect data from their sensors. That data is used to train improved models, and those models are then deployed back to the vehicles.
Chinese systems increasingly use continual learning approaches where the vehicle's AI is constantly being refined based on real-time feedback from the broader transportation ecosystem. There's less separation between training and deployment.
This technical divergence creates very different development trajectories. American systems tend to improve through step functions, periodic updates that significantly enhance capabilities. Chinese systems improve more continuously with smaller but more frequent advancements.
And these different technical approaches create distinct safety philosophies. American systems emphasize what's called fault tolerance, the ability to handle any situation safely, even when things go wrong.
Chinese systems increasingly rely on distributed safety. The idea that safety emerges from the coordinated behavior of multiple actors in the transportation system, not just from individual vehicle capabilities.
By 2025, these divergent approaches were producing autonomous vehicles with very different characteristics. American systems excelled in complex, unstructured environments, but at high cost. Chinese systems thrived in structured, connected environments at lower cost.
And this technical divergence directly impacts automakers' design and engineering decisions. Do you optimize your vehicle architecture for high-power onboard computing, or do you design for connectivity and integration with external systems?
The answer increasingly depends on where you expect your vehicles to operate. In markets with developed V2X infrastructure, the Chinese approach offers advantages. In markets without such infrastructure, the American approach may be the only viable option.
But the most fascinating aspect of this technical divergence is how it's playing out in different geographies. Because while China and the US were developing their distinct approaches, the rest of the world was making choices about which model to adopt.
While the US and China were developing their different approaches to automotive AI, something interesting was happening in the developing world. Countries across Africa, Southeast Asia, and Latin America were making choices about which automotive AI ecosystems to adopt.
And these choices weren't necessarily driven by geopolitical alignment. They were often based on practical considerations: cost, accessibility, and adaptability to local conditions.
Take Kenya, for example. In 2023, Kenya's Ministry of Transport partnered with Chinese companies to develop smart traffic management systems for Nairobi. The project includes AI-powered traffic lights, congestion prediction, and eventually support for autonomous vehicles.
But what's notable is that Kenya isn't just buying Chinese technology. Kenyan engineers are being trained to customize and maintain these systems. There's a significant knowledge transfer component.
Or consider Brazil's approach. Rather than choosing between American and Chinese systems, Brazil is experimenting with hybrid approaches. They're using Chinese infrastructure solutions but integrating them with Western vehicle technology.
This pragmatic approach is increasingly common. Countries are treating automotive AI as modular, adopting different components from different sources based on their specific needs and constraints.
And this creates interesting dynamics for global automakers. A company like Volkswagen needs to ensure its vehicles can operate in both American and Chinese automotive AI ecosystems, as well as in the hybrid systems emerging in other markets.
This has led to the development of what the industry calls adaptable autonomy stacks, vehicle systems that can interface with different external infrastructure depending on what's available.
By 2024, most major automakers were designing vehicles with these adaptable systems. They might use their own proprietary AI when operating independently, but switch to local infrastructure-supported modes when available.
And this adaptability extends to how vehicles are marketed and sold. The same physical vehicle might be positioned as a self-contained autonomous system in the US, but as part of an integrated smart transportation ecosystem in China.
This creates fascinating business model implications. In markets with Chinese-style infrastructure, automakers can potentially offer lower-cost vehicles with fewer onboard sensors and less computing power, relying instead on the ambient intelligence of the transportation system.
In markets with American-style independence, those same automakers need to equip vehicles with more sensors, more computing power, and more sophisticated onboard AI, all of which increase cost.
What we're seeing is a kind of automotive AI regionalization. Different regions are developing distinct approaches based on their existing infrastructure, regulatory frameworks, and strategic priorities.
And this directly impacts how autonomous vehicles are deployed. In regions with Chinese-style infrastructure, we're seeing more widespread deployment, but with more geographical constraints. These vehicles work well within their designed environments, but may struggle outside them.
In regions with American-style independent vehicles, deployment is often more limited initially, but with fewer geographical constraints. These vehicles can theoretically operate anywhere, but require more validation before widespread deployment.
By 2025, this regionalization was creating what some analysts call autonomy islands, specific geographic areas where autonomous vehicles can operate seamlessly, but with limited interoperability between regions.
And this brings us to the question of standards and interoperability. Because if different regions develop incompatible automotive AI ecosystems, it creates significant challenges for global mobility.
Imagine a world where your autonomous vehicle works perfectly in one city, but needs to be replaced or significantly modified to operate in another. That's the risk of divergent standards.
This is why organizations like the International Organization for Standardization, ISO, and the Society of Automotive Engineers, SAE, have been working to develop global standards for autonomous vehicles and intelligent transportation systems.
But progress has been slow, in part because these standards processes are themselves becoming battlegrounds between American and Chinese approaches.
Which brings us to Canada's position in all of this, because while the US and China are competing for global influence, Canada finds itself in a unique and potentially valuable position as a bridge between these different approaches.
So where does Canada fit in this global competition to control the future of automotive AI? The country that invented the foundational technology, but has watched much of the commercialization happen elsewhere.
It's a complex position. On one hand, Canada has tremendous advantages. The Toronto-Waterloo corridor remains one of the world's leading AI research hubs. The Canadian AI ecosystem continues to produce cutting-edge research in computer vision, reinforcement learning, and other fields crucial for autonomous vehicles.
Companies like Waabi, founded by Raquel Urtasun, who previously led Uber's self-driving efforts, are developing innovative approaches to autonomous driving. Waabi's simulation-first approach could significantly reduce the need for expensive real-world testing.
And Canada's research institutions continue to attract global talent. The Vector Institute in Toronto, Miller in Montreal, and AMI in Edmonton form a national network of AI excellence that punches well above its weight in global influence.
But Canada faces significant challenges. The persistent brain drain of top talent to American companies remains a problem, and Canadian companies often struggle to scale their innovations globally.
The most intriguing possibility is that Canada could develop a distinctive third approach to automotive AI, one that draws on the strengths of both American and Chinese models while avoiding their weaknesses.
What might that look like in practice? One emerging Canadian approach emphasizes what's called federated learning, a technique that allows AI models to improve without sharing raw data.
This could address one of the key tensions between American and Chinese approaches. American systems prioritize privacy but struggle with data limitations. Chinese systems benefit from massive data sharing but raise privacy concerns.
Federated learning allows vehicles to learn collectively while keeping sensitive data local. Each vehicle learns from its own experiences, shares only the insights, not the raw data, and benefits from other vehicles' insights.
Canadian researchers at the University of Waterloo and the University of Toronto have been pioneers in applying federated learning to autonomous vehicles. Their work could form the foundation for a distinctively Canadian approach to automotive AI.
Another area where Canada is carving out a unique position is in AI safety and ethics. As autonomous vehicles become more widespread, ensuring they're safe, reliable, and trustworthy becomes crucial.
Canada's research institutions are leading in AI safety research. The Vector Institute, Miller, and the University of Toronto are producing important work on making AI systems interpretable, robust, and aligned with human values.
This focus on safety and ethics could be a significant advantage as autonomous vehicles move from technical novelties to mainstream transportation options. Consumers and regulators alike are increasingly concerned about the safety and trustworthiness of autonomous systems.
There's also the potential for Canada to become a neutral testing ground for international automotive AI standards. As a country with strong relationships with both the US and China, Canada could serve as a bridge between different approaches.
Canadian cities like Toronto, Montreal, and Vancouver could become living laboratories where different automotive AI ecosystems are tested and integrated. The diverse geography and climate conditions of Canada make it an ideal testing environment for systems that need to work in varied conditions.
But perhaps the most promising aspect of Canada's position is its potential role in what some call responsible AI innovation, developing automotive AI systems that balance technological advancement with social, ethical, and environmental considerations.
This isn't just about avoiding harm, it's about actively designing automotive AI systems that contribute to societal goals like reducing emissions, improving accessibility, and enhancing road safety.
Canadian projects like the Responsible AI for Autonomous Vehicles initiative at the University of Toronto are exploring how to embed these considerations into the design of automotive AI systems from the ground up, rather than treating them as afterthoughts.
And this focus on responsibility could be Canada's most valuable contribution to the global automotive AI landscape. As autonomous vehicles move from technical experiments to critical infrastructure, questions of responsibility, accountability, and social impact become increasingly important.
The challenge for Canada is translating these research strengths into commercial impact. It's not enough to develop innovative approaches. They need to be deployed at scale to influence the global trajectory of automotive AI.
This is where policy becomes crucial. Canada needs a coordinated national strategy that treats automotive AI as a strategic priority, not just an interesting research area.
By 2025, there were promising signs of such a strategy emerging. The Pan-Canadian Artificial Intelligence Strategy was updated to specifically address autonomous systems, including vehicles, and new funding was allocated for commercialization, not just research.
But the window for Canada to establish a distinctive position in the global automotive AI landscape is narrowing. The industry is making long-term technology bets right now. If Canada wants to influence those decisions, it needs to act decisively.
The opportunity is real. The foundational technology came from Canada. The research expertise is still here. The question is whether Canada can build on that foundation to create a globally influential automotive AI ecosystem.
Or whether it will remain primarily a producer of talent and research for other countries' automotive AI ambitions.
Before we reach our conclusion, let's consider what all of this means for actual drivers, for people who will be using these automotive AI systems in their daily lives.
We've spent much of this episode discussing geopolitics, technical approaches, and strategic competition. But at the end of the day, what matters most is how these different approaches to automotive AI will affect the everyday experience of drivers and passengers.
The American approach to automotive AI, with its emphasis on self-contained intelligence, creates a particular kind of user experience. Your vehicle is your vehicle. It learns your preferences, your routes, your habits, but that information generally stays with you.
The driving experience in an American-style autonomous vehicle is often described as having a superhuman chauffeur. The vehicle can handle complex situations independently, adapt to your preferences, and provide a highly personalized experience.
But that independence comes with limitations. Without access to broader infrastructure intelligence, the vehicle might not always know about traffic conditions beyond its sensor range, or construction that appeared overnight, or the intentions of other road users.
In contrast, the Chinese approach, with its emphasis on ecosystem integration, creates a very different experience. Your vehicle is part of a coordinated system. It knows about traffic conditions miles ahead. It understands the intentions of other vehicles. It can negotiate priority at intersections with the infrastructure itself.
The driving experience in a Chinese-style connected autonomous vehicle is more like being part of a choreographed dance. The vehicle moves smoothly through traffic because it's coordinating with the entire system, not just reacting to what it can directly sense.
But this coordination comes with its own trade-offs. The system might optimize for collective efficiency rather than individual preference. Your vehicle might take a longer route to avoid contributing to congestion elsewhere, or it might yield priority to emergency vehicles or public transit.
And then there's the Canadian approach, still emerging but potentially distinct. It emphasizes responsible autonomy, systems that are transparent about their limitations, that explain their decisions, that balance individual preference with collective well-being.
The driving experience in a Canadian-style responsible autonomous vehicle might be more collaborative. The vehicle would handle routine driving tasks, but involve you in decisions that have ethical dimensions or that involve trade-offs between efficiency and other values.
These different approaches also create different relationships between drivers and their vehicles. In the American model, the vehicle is often positioned as your personal assistant or chauffeur, serving your needs and preferences above all else.
In the Chinese model, the vehicle is more like a node in a network, part of a larger system optimized for collective outcomes, with your individual preferences balanced against system-wide efficiency.
And in the emerging Canadian model, the vehicle might be more like a partner, handling routine tasks independently, but engaging you in a collaborative relationship for more complex or consequential decisions.
These philosophical differences directly impact how these systems are marketed and sold. American automotive AI companies often emphasize personal freedom, convenience, and customization. Chinese companies emphasize efficiency, reliability, and integration. Canadian approaches might emphasize responsibility, transparency, and balance.
And these differences extend to how autonomous vehicles are integrated into broader transportation systems. In the American model, autonomous vehicles are often seen as direct replacements for privately owned human-driven cars, preserving the existing transportation paradigm but making it more convenient.
In the Chinese model, autonomous vehicles are more often seen as components of a reimagined transportation ecosystem, potentially challenging traditional car ownership with new models like robotaxis, shared shuttles, and mobility-as-a-service offerings.
The Canadian approach might emphasize what some researchers call mobility justice, ensuring that autonomous transportation systems serve all members of society equitably, including those with disabilities, the elderly, and those in underserved communities.
These different visions for how autonomous vehicles should be integrated into society reflect deeper cultural and political values. The American emphasis on individual choice and market-driven solutions. The Chinese emphasis on collective efficiency and state coordination. The Canadian emphasis on inclusivity and social responsibility.
And for drivers around the world, the experience of autonomous vehicles will increasingly be shaped by these competing visions and the values they embed. The autonomous vehicle you drive, or that drives you, won't just reflect technical choices, but philosophical ones.
As we move toward a world where AI increasingly controls our vehicles and transportation systems, these philosophical choices become more consequential. They shape not just how we drive, but how we live, work, and interact with our built environment.
Which brings us to the conclusion of our journey, from the neural networks pioneered in Toronto laboratories to the global competition to control the future of automotive AI.
As we wrap up today's deep dive into the automotive AI race between two empires, it's worth remembering that this story is still being written. The technologies, the strategies, the competitive dynamics, they're all evolving rapidly.
The AlphaGo match in 2016 started as a contest over an ancient board game. 9 years later, it's clear the real game is over the rules. For technology, for society, for the very process of how we move through the world.
China and the West have built two distinct automotive AI visions, not just in architecture or deployment, but in philosophy. The US, emphasizing individual vehicle intelligence, market-driven innovation, and proprietary technology. China, emphasizing ecosystem integration, state coordination, and strategic openness.
Yet both journeys remain incomplete and deeply entangled. Supply chains, talent flows, global research conferences, they blur walls as fast as empires can build them.
And Canada, the birthplace of the neural networks that power modern automotive AI, finds itself at a crossroads. Will it leverage its foundational role to create a distinctive third way? Or will it remain primarily a supplier of talent and research to the American and Chinese automotive AI ecosystems?
The answer depends on choices being made right now by researchers, companies, investors, and policymakers. The window for Canada to establish a distinctive position in the global automotive AI landscape is narrowing, but the opportunity is real.
Canadian AI pioneer Geoffrey Hinton, now the field's elder conscience, issued a warning in a lecture from the Toronto-Waterloo corridor in late 2024. We're building something more powerful than any engine or weapon. The question isn't only who leads, but whose values get encoded and whether wisdom can keep up with ambition.
As first movers battle for dominance, the frontiers of automotive AI will be shaped by adoption, norms, and the creativity of billions across Toronto, Hangzhou, San Francisco, Lagos, and beyond.
In a world where code crosses borders faster than treaties or armies ever did, the real test is whether AI for all becomes reality in our vehicles and transportation systems, or merely rhetoric.
The next chapter, as always, is unwritten, but it's being written right now in labs and boardrooms and government offices around the world. And the decisions being made today will determine whether your next car thinks like Silicon Valley, coordinates like Shenzhen, or bridges both worlds like Canada.
AutoAgentic is pioneering AI-driven solutions that help automotive dealerships streamline operations, optimize sales performance, and elevate customer experiences. With our human-centered approach and over 90 specialized AI agents, We're not just delivering technology, we're delivering trusted guidance for the rapidly evolving automotive landscape.
We'd like to thank our producer, Barry Hillier, co-founder and CEO of AutoAgentic AI, whose vision for intelligent automotive solutions continues to inspire our exploration of these transformative technologies.
If you'd like to reach out with suggestions for future episodes or share your thoughts on today's deep dive into automotive AI empires, email us at barry@autoagentic.ai. Barry is always on the lookout for exciting new topics, companies, and people shaping the future of mobility.
This episode was produced by the team at AutoAgentic. Learn more at autoagentic.ai.
Thanks for joining us on this journey through the automotive AI landscape. Until next time, keep thinking about how intelligence is reshaping the way we move.